So let's work on this next set of problems here, and we're going to be learning all about the eye and corrective lenses and that stuff. So first, there are a couple of really important things that I have written out here, and it's that when we're dealing with the eye's lens, so first of all, the eye's lens is a convex lens. It is shaped like this, right? So when dealing with the eye's lens, the image forms on the retina. So if the image is forming on the retina, the image distance is going to be Q equals plus 2 centimeters. So that's a constant. That's just the size of a person's eye. Okay, next, myopia. What does myopia mean? It means nearsighted. So you can only see things that are close. Therefore, you have a far point. That's the point where you can't see anything further than that. So a corrective lens, the whole point of it is used to see objects that are further away from your far point. So when objects are at infinity. And in that case, we use Q, our image, equals negative far point. So we'll do some examples and see what that means. Lastly, hyperopia means you're farsighted, so you can only see far away, and you have a near point, so you can't see anything closer than your near point. And the whole point of a corrective lens, it's used to see objects up close. So your object is going to be located at some distance. So that's why I have P equals a number. And for that, Q equals negative near point. Okay, so let's get started. A particular nearsighted patient, so they can only see close, they have a far point, can't see objects, so a far point, can't see objects clearly when they are beyond 25 centimeters. So the far point is 25 centimeters. For A, what focal length should this prescribed contact lens have to correct the problem? So we're looking for focal point. Find the power of the lens in diopters. The symbol for that is, let's see. Oh, so the symbol for power is S, and it's measured in diopters, or inverse meters. Okay, so let's try and make sense of this problem. We have a nearsighted person that has a far point, and we're trying to figure out the focal length of the corrective lens. Okay, so in that case, we want to be able to see objects that are at infinity. Okay, and our Q will be negative 25 centimeters. So this is, what I'm getting this from is what I have as number 2. So 1 over F, and we'll use the lens maker's equation for this, equals 1 over P, so infinity, plus 1 over Q, negative 25 centimeters. So this will just equal 0, and we can take the inverse of both sides. So F equals negative 25 centimeters. Okay? And so from there, we need to convert this to meters. So F equals negative 0.25 meters. Okay, so now that we have the focal length, we can find part B, the strength or the power of the corrective lens. So we take 1 divided by F, and F must be in meters. So the power is 1 divided by negative 0.25. And we find that the power should be negative 4 diopters, which is the symbol for D, diopters. Okay? And also, what does this mean? So we have a negative focal length. So let me actually draw this out. So what's happening for someone that is, in this case, nearsighted, they have myopia, and it means that their lens is converging their eyes too short of the retina back there. So the rays are converging too soon. And to correct this, let's think, what type of lens would we use? So if the image is forming too soon, we need to put a diverging lens there. And this is not the best drawing, but it will look like this. So that it instead focuses at the retina where it should. Okay? So let's look at a next example. The near point of a patient's eye is 50 centimeters. So if they have a near point, that means they're farsighted. They can only see far away. For A, what focal length must a corrective lens have to enable the eye to see clearly, to clearly see an object 25 centimeters away? Okay, so we're trying to solve for F, the focal length. We know that the object is 25 centimeters away. Okay, and for part B, we're also going to find the power in diopters. Okay, so let's look at our other scenario we have. So we have a near point, that means we're farsighted. Okay, and in that case, our corrective lens will be used to see close, right? So we're looking for an object at 25 centimeters, and Q will be the negative of the near point. So Q equals negative 50 centimeters. So let's calculate the focal length. Focal length equals 1 divided by P, 25, plus 1 divided by negative 50, and the inverse of that. So let's see what our calculator tells us. 1 divided by 25, in this case we can just do minus 1 divided by 50, and then take the inverse of that. So we get that the focal length should be 50 centimeters. Okay? And in that case, the focal length is 0.5 meters. Okay? So the strength will be 1 divided by 0.5. So it'll be 2 diopters. Draw this a little better. 2 diopters. Okay? Next. So the accommodation limits for nearsighted Nick's eyes are 18 centimeters and 80 centimeters. When he wears his glasses, he is able to see faraway objects. At what minimum distance is he able to see objects clearly? Okay, so let's begin with what these are. So we're talking about nearsighted Nick's eyes, so that's important. His near point is 18 centimeters. His far point equals 80 centimeters. So those are the accommodation limits. So that's what accommodation limits means. It means your near point and your far point. When he wears his glasses, he is able to see faraway objects clearly. Okay, so he can see far, so he's nearsighted. Okay, at what minimum distance is he able to see objects clearly? So we're going to be looking for P. Okay, and when he wears his glasses, so P equals infinity. Okay, so let's again look at our rules. So if he's nearsighted, he has a far point, which is going to be negative 80. So yeah, he can see far away clearly. Q will equal negative 80. And from this we can figure out the focal length. So 1 divided by infinity is 0. Plus 1 divided by negative 80 inverse. So the focal length is going to be negative 80 centimeters. And now that we have the focal length, we can use this for the next part of the question. Now we're looking for P, where he can see objects clearly. So in that case, we have 1 over negative 80 equals 1 over P plus 1 over, and now what will we use for Q? We have to use negative 18. Okay, so for P equals 1 over negative 80 minus 1 over negative 18 inverted. So let's see what our calculator gives us. 1 divided by negative 80 minus 1 divided by negative 18. The inverse of that is 23.225 centimeters. Okay, so that is how you solve that problem. It's a little bit tricky. Next, a certain child's near point is 10 centimeters, so they straight away give us the near point. Her far point with eyes relaxed. Okay, eyes relaxed means far point equals 125 centimeters. Each eye lens is 2 centimeters from the retina. Okay, so that's that constant. Part A, between what limits measured in diopters does the power of the lens to cornea combination vary? Okay, so we're looking for strength using near point and the strength using far point. Okay, so this makes sense. So strength is 1 over the focal length. So to find the focal length using near point, we'd use this. So 1 over F equals, so let's go back to our list. For dealing with a near point, P will equal a number. Oh, okay, we're dealing with this child's eye. So the retina, the image will form at the retina. Okay, so 1 over 2 centimeters plus 1 over 10 centimeters. Okay, so let's see what our calculator gives us for F. So 1 divided by 2 plus 1 divided by 10. And then the inverse of that, we get that the focal point is 1.6 repeating centimeters. Okay, and then find S from that, we take 1 divided by 0.016 repeating meters. Okay, so we get 60 diopters. Okay, and now let's do the same thing for the other accommodation limit. So the image is forming at the retina, and now we can use the far point. So we find that the focal point is 1 divided by 2 plus 1 divided by 125, and the inverse of that, make sure we take the inverse, is 1.97 centimeters. Okay, so to find the strength, we need 0.0197 meters. Okay, so let's calculate this. And I get 50.8 diopters. Okay, so for part A, between what limits measured in diopters does the power of the lens to cornea accommodation vary? So that is the range. So the range is 50.8 to 60 diopters. Okay, for B, calculate the power of the eyeglass lens the child should use for relaxed distance vision. Okay, so this comes back to this point here. So with eyes relaxed vision means you're looking far away. Okay, so you want to see objects at infinity. Okay, so in that case, let's look at our rules. So yeah, she has a far point, and we want to see objects at infinity. So Q will equal negative far point. So Q equals negative 125 now. Okay, so we're calculating the power of the corrective lens. So in this case, we can find the focal length of the corrective lens to be 1 over infinity, which is just 0, plus 1 over negative 125 centimeters. Okay, inverted. So F corrective, the focal length is negative 125 centimeters, or negative 1.25 meters. So the strength of that lens, strength of the corrective lens, equals 1 divided by negative 1.25. So let's see what that is. 1 divided by negative 1.25, okay, is negative 0.8 diopters. Okay, so now the question is the lens converging or diverging? Okay, so we can get our answer from the focal length being negative, but let's also just think about this conceptually. So we're calculating the power of the corrective lens the child should use for relaxed distance vision. So this is helping her see far away. So if you were to need help seeing far away, it means you're nearsighted. So that means you have myopia, right? So going back here, if you have myopia, you're nearsighted. That means you have a far point and you need help seeing far away. Okay, so in that case, this is what we're dealing with right here. we would need a diverging lens. And we could also have just known that by the focal length being negative. Alright, sorry if this video is a little tricky. These can sometimes get confusing, but thank you for watching.